Hello everyone, welcome to the third lecture on electrostatics. In the second lecture on electrostatics, we have learned that the charges interact with each other. That means the charges exerts force on each other. This force can either be attractive or repulsive depending on the nature of the interacting charges. Due to the force, the objects or the particles or the charges in our case either move towards each other or fly away from each other depending on the nature of the force. But it is not always necessary for the objects or the particles to either move towards each other or away from each other even when the forces are acting. Sometimes the particles or the charges or the objects stay still even though multiple forces acts on them. This interesting state of the object or the particles of the system is called equilibrium. In this video, we are going to learn about the concept of equilibrium. We'll also discuss some examples on equilibrium in collaboration with Coulomb's law. So yes, my name is Vijay Krishna and you're watching up his channel. Let's get started. First, let's learn the concept of equilibrium. Okay, equilibrium is basically of two types: translational equilibrium and rotational equilibrium. This classification is done based on the nature of the motion. So, if the nature of the motion is translational, then we apply translational equilibrium. If the nature of the motion is rotational, then we apply rotational equilibrium. Okay, right. Let's understand what is translational equilibrium and how do we apply it. Okay, so translational equilibrium is nothing but if we take an object, when the net force acting on the object is 0, there are multiple forces acts on the object, right? So even though multiple forces are acting on the object, individual forces acting on the object, however, the net force on the system is 0, then we say the object is in translational equilibrium. So let's F net force acting on the system is 0. When the net force acting on the system is 0, then we say that object or the system is in translational equilibrium. Okay. If the net force acting on the system is 0, as we all know, F net is equal to MA. If this F net is equal to 0, then MA also must be equal to 0. Since mass cannot be equal to 0, since the object will have a certain amount of mass, whether it may be 0.1 or 10 kg, so or any other value, acceleration should be equal to 0. For the object to be in translational equilibrium, net force to be 0, net force is supposed to be 0 and acceleration also must be equal to 0. Okay. So as the acceleration is defined as rate of change of velocity, this acceleration could possibly be 0 when v is equal to 0 or v should be constant. So, if the system is in translational equilibrium, then the net force acting on the system must be equal to 0, or the acceleration of the system is equal to 0, or either the particle or the object or the system is at rest, or it is moving with uniform velocity. So these are the points which we use to identify whether the system or the particle or the body is in translational equilibrium or not. If the body has net force 0, then the body is said to be translational equilibrium. If the body is moving with uniform velocity, then also we consider the body is in translational equilibrium. Hope the points that I have discussed is clear to you, right? Okay. So this is about translational equilibrium. Let's understand one more point. What is the meaning of net force is equal to 0? Okay, let me explain this point. I'm taking an object. So this is the floor on which there is a box. There is a box of mass m, let's say. Okay, the weight of the object is acting vertically downwards, whereas the floor is applying a certain amount of force called normal force perpendicular to the surface against the gravity. However, this object is not moving. I have assumed that the object is at rest. So if the object is at rest, then net force on the system must be equal to 0 as per the discussion that we have here. Okay, how this net force can be 0? Why this object is in rest? Okay, even though there are two forces acting on the object. This is because the normal force is balancing the mg. That means the vector sum of all the forces on the system or the object, on the system or the object, on the system or the object is 0. It must be 0. Okay, so not individual forces are 0. The vector sum of all the forces must be equal to 0. Then only we say the net force on the system is 0. Then only we say the acceleration of the system is 0. If the acceleration of the system is 0, either the object is at rest as per the discussion that we had here, or the object moving at a constant velocity. Okay, so this is all about translational equilibrium. Whenever we come across translational equilibrium, we have to consider the net force on the system is 0. Okay, now coming to the second case of equilibrium, that is translational equilibrium. So this kind of equilibrium we observe in case of rotational motion. Okay, right, let's understand this translational motion also, but in this lecture we mostly use translational equilibrium. But anyhow, let's understand this rotational equilibrium as well. Okay, according to rotational equilibrium, the net torque acting on the object or the system is equal to 0. So net torque on the system must be equal to 0. How can we say the net torque is 0? And one more thing that I wanted to tell you, this torque net is equal to I alpha, where I is moment of inertia and alpha is angular acceleration. So I of the object, moment of inertia of the object cannot be 0 because the objects have certain shape or size and mass. Okay, so the I cannot be 0. So alpha can possibly be 0. As net torque on the system is 0, I cannot be 0. So alpha must be equal to 0 if the object or the system is said to be in rotational equilibrium. Hope my point is clear to you, right? Okay, so alpha is equal to 0. This alpha is usually written as, defined as rate of change of angular velocity. So this alpha can possibly be 0 only when omega is equal to 0 or omega is equal to constant. So differentiation of constant is 0, right? So omega is constant, that means differentiation of constant could be 0, and if omega is 0, then also alpha must be equal to 0. So these are the two cases where the object can be in rotational equilibrium. So whenever the object is said to be in rotational equilibrium, then we say the net torque acting on the system or the object is equal to 0, which resulted in alpha 0 and either omega 0 or angular velocity is constant. Okay, similarly we have the explanation that we had in translational equilibrium, vector sum of all the forces on the system or the object is 0. In this case, in rotational equilibrium, we define this as vector sum of all the torques on the system must be equal to 0. Whenever we say the net torque on the system is 0, means the vector sum of all the torques on the system must be equal to 0. Okay, right. So, and these are the points that we have already written here. Net force on the system is 0, acceleration of the system must be 0 and the object either at rest or moving with constant velocity. Similarly, for the rotational equilibrium also, net torque 0, angular acceleration 0, and the object is either at rest or rotating with constant angular velocity. Right? Hope you have understood the explanation about this slide. Right? Let's move on to the next slide. Again, this equilibrium classified into 3 types. Those 3 types are represented here, shown here: stable equilibrium, unstable equilibrium, and neutral equilibrium. Let's understand one after the other. Okay. So first, stable equilibrium. Let us suppose an object is at rest. An object is at rest. For example, I have taken a spring which is held about a support point. Okay, and I have attached a mass and I left it slowly. Okay, I left it slowly. Then what happened? This spring has stretched for some length, and then the block came to rest, or the object came to rest at some point after some elongation. Then what happens? The object is not moving. That means the object is at equilibrium, is in equilibrium. Okay, is at rest. That means it is in equilibrium. So as the object is in equilibrium, the net force on the object must be equal to 0. Right? So net force on the object is equal to 0. Right? Okay, that we have understood. Okay. Now the point is, if I have taken that object and let's say I have slightly displaced that object from the equilibrium position, slightly, then left it free. Then what happens? This object will move up and down, about the mean position, or the equilibrium position, right? Up and down about the equilibrium position, right? So that means the object is always trying to come to the equilibrium point or equilibrium position. This kind of equilibrium is called stable equilibrium. If the object is displaced from the equilibrium position slightly, then the object tries to comes to equilibrium position, then we say that equilibrium position or that type of equilibrium is stable equilibrium. As you can see in the illustration, first illustration, we have stable equilibrium illustration. Let's say we have a bowl. And in that bowl, I have placed a marble that we play. Okay, marble. I have placed in the bowl. Now what I am doing is, I am taking this marble and I am slightly displacing this marble to some extent. Slightly displacing this marble to some extent. Then what happens? I left it free. Then exactly what happens? This marble right here, which is displaced from the equilibrium position, again tries to comes back to its equilibrium position and moves up and moves down and moves up, moves down, moves up and down. But anyhow, this marble, which is in equilibrium at the very beginning, when I have displaced, it is trying to come to its equilibrium position always. Okay, as this object or the marble in our case is trying to come to its equilibrium position, we say that kind of equilibrium is called stable equilibrium. Okay, so definition is right here. Object is slightly displaced, and it tries to returns to its original position. Then we say the equilibrium is called stable equilibrium. Now coming to the second case of equilibrium, which is unstable equilibrium. In this case, let's say I have displaced the object slightly. Then if it is not coming back, rather it is moving away. Let me give you an example. I have taken the illustration here. So this is again a bowl that I have taken. Okay, and again the marble that I have taken, I kept it exactly on the top of the bowl. Okay, this time the bowl is reversed. Okay, so I kept it exactly on top of this bowl. Now let's say this system is in equilibrium. The marble is not moving, which is exactly at rest, and the entire system is in equilibrium. Now what I am doing is, I am just giving a slight push, or I have displaced this object slightly, little amount of displacement. Then what happens? It has to come back for if the equilibrium is stable equilibrium. But in this case, the marble will not come back, but it again continues to fall down. continues to fall down. It is moving away from the equilibrium, continuously moving away from the equilibrium. This kind of equilibrium is called unstable equilibrium. Unstable equilibrium. So, if the object is slightly displaced, object continues to move away, from the equilibrium position. This kind of equilibrium is called unstable equilibrium. Okay. Now coming to the third kind of equilibrium, neutral equilibrium. Neutral equilibrium. In this case, let's say I have placed this marble on the flat surface. Okay. Now what I am doing is, this is at rest, marble is at rest, floor is again at rest. That means the entire system is at rest. That means it is in equilibrium. This system is in equilibrium. Now what I am going to do is, I am going to displace this marble slightly, give a slight push, or displace it and keep it here. Keep it here. What I am doing is, I'm displacing this object slightly, slowly to this point. Then what happens? This marble will stay exactly at where it is. It is neither coming back nor moving away. If it moves away, we call this kind of equilibrium as unstable equilibrium. If it tries to come back to its equilibrium position, then we say that equilibrium is stable equilibrium, as it is not moving away or coming towards the equilibrium position. We say this kind of equilibrium is neutral equilibrium. Okay. Hope all the three types of equilibriums are clearly explained. Hope you have understood. If you find any difficulty in understanding, please comment below or watch it again. Watch it again and again, so that you will be able to understand, you will be able to follow. If you still unable to follow, unable to understand, please comment below. Okay, right. Hope you have understood this entire concept of equilibrium. Let's move on to the examples now. Okay, let's look at the first example. Right. Okay. In this given scenario, I'm going to define the example now. Okay. In this given scenario, we have two spherical objects. These are the two spherical objects, this one and this one, whose masses are equal, which are m and m. Okay, which are held with the help of strings, massless, inextensible strings of length L. Now, what I am going to do exactly is, I am going to give the charge to each of these spheres. I am going to give the equal charges. You can give different charges also, Q1 and Q2, but I am going to give equal charges Q and Q. Now, I am going to give the charges to these objects Q and Q. When the two objects are given with a similar type of charge, then exactly what happens? They repel each other. That means they move away from each other. They move away from each other. Okay. So as they move away from each other, at particular instant of time, they comes to rest. I've shown their final positions. Okay. At this exact location, the net force on these spheres must be equal to 0, because the system is at rest, or the ball or the sphere is at rest. As the sphere is at rest, the acceleration must be equal to 0, thereby the net force on the system must be equal to 0. So this will be in equilibrium and this also will be in equilibrium. Okay. So as the system is in equilibrium, net force acting on the system is 0. This ball is 0. I am going to represent or show all the forces acting on this sphere. Okay. As the sphere has mass, that means it has certain amount of weight, which is acting vertically downwards and given by mg. Right. Now, this negative charge, I am taking this Q and again Q. This Q will exert certain amount of electric force on this Q. That means repulsive force. That means this sphere is repelling this sphere in this direction. This is the electric force. Fe, I'm stating it as Fe. This Fe is equal to Coulomb's constant K, Q1, Q2 by, let's suppose this distance is R. Separation between the two charges, I am considering it as R. Now take Q square by R square is the electric force between the two charges, repulsive force between the two charges according to Coulomb's law. Now, this weight and electric force, developing certain amount of tension in the string, which is T. Now, as the strings are vertical at the very beginning, due to the repulsive force, the strings are moving away from each other. That means they are making certain angle with respect to vertical. I'm considering that angle as theta. If this angle is theta, this angle also should be theta. Right? Okay. Now I'm going to use, in order to balance the forces, I'm going to resolve the, tension force. So in order to resolve the tension, I'm going to draw x and y axis. Horizontal axis as x axis, vertical axis as y axis. This T, if this angle is theta, this angle also should be theta. Now T can be resolved into two components. Here in this side, T cos theta will come, and this side, T sin theta will come. Okay. Now from this diagram, we can understand that T sin theta is balancing electric force, electrostatic force, and T cos theta is balancing the weight of the object. I have got two equations. This Fe can be replaced with K Q square by R square mg. I'm considering this equation as 1 and this equation as 2. By using these two equations, we can simplify further to find the unknown quantities when the rest of the quantities are given to us. Let's even simplify further. Okay, right. Now what I'm going to do is, in order to get the angle with which the strings, the strings making with the vertical. Okay. Now let's say equation 1 divided by 2. Let's find the angle. Equation 1 divided by 2. Now equation 1 is T sin theta is equal to K Q square upon R square, divided by 2 is T cos theta is equal to mg. This T and T will get cancelled. What we got is tan theta is equal to K Q square by mg R square. So this is one important relation where we can find the angle made by the strings with the vertical, where K is Coulomb's constant, Q is charge on each sphere. I have already told you, I have taken the equal amount of charge, I have given the equal amount of charge to both the spheres, but you can give different charges as well. Okay, let's say you have given Q1 charge to one sphere, Q2 charge to other sphere. In such a case, Fe must be equal to K Q1 Q2 by R square. And here you will get K Q1 Q2 by mg R square. So that is the only difference. Rest of the things will be same as it is, will remains the same. Okay. Now let's simplify even further. Okay, as the separation between the two objects is not given, final separation between the two spheres is not given, R is not given. If R is not given, we can find R value in terms of given quantities like L and theta. If this length is L, then this length also must be equal to L, which are making angles theta and theta. Okay, so L, what would be this side? If this is theta, this must be theta, and L sin theta will come this side. Okay, and this side also L sin theta. Okay, L sin theta is this length and L sin theta is again this length. Total R can be written as 2L sin theta. Instead of R, I can replace R with 2L sin theta here. What am I getting? Tan theta is equal to K Q square by mg R can be written as 2L. I'm directly writing R square can be written as 4L square sine square theta. 4L square sine square theta. Okay, right. Now, as we have got, another conclusion here, you can even further, even simplify this equation by considering some, special cases like theta is very small. Theta is, if theta is very small, if theta is very small, then tan theta and sine theta, tan theta is identically equal to sine theta is identically equal to theta, right? If you replace theta in place of tan theta and sine theta, what you will get? So theta is equal to k q square by mg theta square, sorry, 4L square mg theta square. Now theta square can be taken this side, you will get theta cube is equal to k q square by 4L square mg. You can find theta from this equation also. So remember one point, this analysis only if theta is very small. Theta is very small. If theta is considerably large, then we supposed to use this equation. Okay. If theta is very small, then we use this relation. Hope you have understood the entire analysis that I have made here about equilibrium of the sphere. I have analyzed only one sphere. I haven't analyzed the second sphere. It is because the same analysis goes to the second sphere as well due to symmetry. Because whatever the force exerted by this sphere on this one is just same as the force exerted by this sphere on this one. Right? Electric forces are same. Since the masses that I have taken as same, the weights also same, the tension developed also must be equal. Right? That is the reason I have analyzed only one sphere. The same analysis goes to the second sphere as well. Still, if you want to analyze these two equations, fundamental equations, you don't need to remember all these analysis. You just remember these two equations. Okay, then you will be able to solve any kind of question that you have been asked to. Okay. Now what I am going to do is I am going to simplify or analyze these two equations even further. Okay, I am going to erase these things. Right. Okay. 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 Right. Let's simplify even further. So T cos theta is equal to mg, which is equation number 2. Now instead of finding theta or tan theta or replacing r with 2L sin theta, I just wanted to find the tension developed in the strings. In order to find the tension, what I'm going to do is I'm going to square each equation and add them. That means equation 1 square plus equation 2 square. Equation 1 square and 2 square. Now, if equation 1 square gives t square sine square theta is equal to k square q to the power 4 by r to the power 4. Okay. Now, plus 2 square, that means t square cos square theta is equal to mg. Instead of writing the entire equation, terms, what I am going to do is I am going to simply write fe square. T sin theta whole square means t square sin square theta is equal to fe square, and t cos theta whole square means t square cos square theta plus mg whole square. mg whole square. right? Now, if I take t square common, I'll get t square is equal to sine square theta plus cos square theta is equal to fe square plus mg whole square. Now, this entire thing will be equal to sine square theta plus cos square theta is equal to 1. Now, what I am getting is t square is equal to fe square plus mg whole square. As t square is equal to fe square plus mg whole square, I am going to write the equation for t as I want to find the tension in the strings fe square plus mg whole square under root. This is one way of finding the tension in the strings, okay, directly without finding the angles and all, okay, right. If you are asked to find the angle, tension, everything, then you can follow the regular method that we have found the angle theta, and then we can substitute the angle theta and the other values which are given to us into the either equation 1 or 2, and we can eliminate theta. I mean, we can find the tension value. Or if you are directly asked to find the tension, you can follow this method. It is much simpler than following the entire steps. Okay, I hope this concept is clear to you. And if you want to make this equilibrium concept, equilibrium example more complicated, little more complicated, you can you can submerge this entire system into any fluid, I'm going to discuss that as well. Okay, let's discuss that one also. Okay, now okay. Okay. Right. Okay. I'm going to draw the free body diagram again. Now this entire system is submerged in a fluid. System is submerged in a fluid of density rho liquid. Okay, rho liquid. Okay, now let's assume density of sphere, rho sphere, let's say rho sphere. Okay, right. Now this entire system now is in fluid or liquid, any liquid. Now what exactly happens? The charge will not change, the amount of charge will not change even if it is placed in any medium. Okay, charge is independent of medium, charge value does not changes with speed or medium. Okay, so even if it is submerged in any kind of liquid or fluid, the charge would remains same q, and mass is also independent of medium, the mass value would also remains same m again. Okay, now I'm going to draw the free body diagram. Weight of the object is acting vertically downwards, which is mg, that we have already learned. Now coming to the next one, this sphere is exerting repulsive electrostatic force on this sphere away. Okay, that is fe. But these two charges are not changing, charges does not change with the medium, but electric force between the two charges changes with the medium. We have learned this in this lecture 2. Okay, so electric force between the two charges changes with the medium. Okay, now this electric force between the two charges is Fe by K, or I can write this as Fe by epsilon r, permittivity of the medium, relative permittivity of the medium, right? Okay. If you want me to recollect, I'm going to write the relations. Electric force between the two charges 1 by 4 pi epsilon naught q1 q2 by r square. If the charges placed in free space, air medium or vacuum medium. Let's say the charges have been placed in some liquid of dielectric constant epsilon r or relative permittivity epsilon r, then the force F dash is equal to 1 by 4 pi epsilon q1 q2 by r. This epsilon can be written as epsilon naught epsilon r. So this equation can be further written as 1 by epsilon r into F F. That means the force will reduce by dielectric constant times. Will reduce by 1 by dielectric constant time. Hope the points are clear to you, right? Now I'm going to take this off. Right. Now let's come back to the actual discussion. Fe by epsilon r. Okay, electric force by epsilon, because when the charge is placed in some medium of dielectric constant epsilon r, then the force reduces by 1 by epsilon r times. Okay, force is this one, weight is acting vertically downwards, and tension will be developed here in the string. In addition to these three forces, there is one more force that is called buoyancy force. Why there is buoyancy force? Because in vacuum medium there won't be any considerable buoyancy force. In air medium there will be buoyancy force, but which is not considerable. But in this case there is a considerable buoyancy force, Fb. Okay, Fb, buoyancy force. This Fb is nothing but density of the fluid or density of the liquid, density of the liquid okay, density of the liquid into volume into G. The volume into G, volume of the submerged portion of the body, or volume of the water, fluid displaced, liquid displaced. Okay. Since the entire sphere is submerged, I am going to take the entire volume of the sphere. Okay, right. Rho L V G. So this is the buoyancy force. But anyhow, the effective weight or the apparent weight means weight apparent is equal to actual weight minus buoyancy force. Actual weight, mass can be written as density into volume. As I have already told you, density of the sphere into volume of the sphere into G. Minus Fb is nothing but density of the liquid, volume into G. Now this volume G, I am taking them as constant, common, rho S minus rho L. I am doing the entire analysis, but I can directly jump onto the conclusions, but I wanted to explain you better so that you can understand it clearly. Okay, so V, volume G, is acceleration due to gravity, rho S is nothing but density of the sphere, rho L is nothing but density of the liquid. Now what I am going to do is volume of the sphere can be written as mass by density of the sphere. As you already know, the relation between density is equal to mass by volume. I wanted to find the volume, so I can write mass by density. As I am writing the volume of the sphere, I am going to take the mass of the sphere and volume of the sphere itself. So mass of the sphere, volume of the, density of the sphere itself, right? So I have written the same relation here. Okay. Now m by rho S, and we have rho S here and rho L again. Now if I want to simplify further, mg is here. I forgot to write it. Mg, rho S by rho S is nothing but 1 minus rho L by rho S. This is the apparent weight. Okay, and we have the effective Fe dash. Fe dash is equal to Fe by epsilon r. In the earlier case, we have used Fe and W, that means weight mg. But in this case, we are going to use Fe dash, and instead of weight, we are using apparent weight here. Okay, but the rest of the procedure would be same. Now let's resolve the tension into this direction. You will get a T. If this angle is theta, this angle also would be theta, T cos theta, and this would be T sin theta. Okay, now I am writing T sin theta is equal to Fe by epsilon naught, this is equation 1, and T cos theta is equal to, what is it? W apparent, which is nothing but mg1 minus rho L by rho S, sorry, rho L by rho L by rho S. This is equation number 2. As we have got two equations, again fundamental equations here, we can solve these two equations in order to find the unknown quantity when the rest of the quantities are given to you. Okay, and if I want to give you some more details about this example. Okay, let's understand this example even further. Let's modify this example little bit modification. Okay, if I would have taken different charges, does the equations change? Yes, of course change, but the concept will not change. Okay, so Q1 Q2, that means Fe would become K Q1 Q2 by R square, Q1 Q2 by R square. As R is not given to us, R can be replaced with 2L sin theta whole square. Okay, this point is clear, right? Okay, now coming to the Fe is equal to K Q1 Q2 by R square. Instead of taking different amount of charges, obviously we won't take opposite polarity charges, because if we take opposite polarity charges, they stick together, right? They don't move away. Okay, so we don't take opposite polarity charges. We are going to take only similar polarity charges. Okay. Now K Q1 Q2 by R square. Instead of taking different charges, let's say we have taken different mass pairs here. If we take different mass pairs, then there is a possibility for the change in angles. In the earlier case, as we have taken same amount of mass for both the spheres, they both will be in equilibrium at the same angles only. Let's say I have taken M1 here and I have taken M2 here. I am holding them like this. I have considered M1 is greater than M2. That means this mass is greater than this mass. As this mass is greater, it will be pulled little bit down. Then the system will be like this. Okay. In such case, if this is M1 and this is M2, I am considering M1 is greater than M2. In such case, this mass will be here and this mass will be somewhere here. That means angle theta 1, angle theta 2, theta 1 is less than theta 2. Okay, but from this further analysis that we have understood that the angles made by the two strings will not always same. They differ according to the masses that have been attached to the strings. Right? I hope you have understood whatever the explanation that I followed through here. Okay. If you still feel difficulty in understanding this example I have analyzed little further. Okay, so that you won't miss any kind of question which comes from this example. Okay, right. I hope this example is clear to you. If you still find any difficulty in understanding this example or explanation, please comment below. Okay, let's move on to the next example of equilibrium. Oh yes, it is a very good example. I am going to define it. You will be able to understand how we are going to solve it. Okay, let's look at the next example. Let's define this example first. I am going to take the two charges. These are the two charges given by Q1 and Q2, which are obviously separated by a distance R. Center to center distance is R. Now, what I am going to consider is Q1 is less than Q2. Why I am taking this, which charge is bigger, which charge is smaller, because you will be able to understand in a bit. Okay. Now, the question is, where should the third charge be placed such that it will be in equilibrium? The third charge will be if not all the charges, only the third charge will be in equilibrium. We have to place the third charge such that it will be in equilibrium. Okay. I am going to divide this diagram into three regions. This is one such region and this is other region, and we have three regions: region 1, region 2 and 3. Region 3. Now let's use our basic common sense and basic understanding of Coulomb's law. to identify the exact location, not exact location, exact region. If we place in that region third object, if we place the third particle in that region, it has to be in equilibrium. Okay, so we have to identify the equilibrium region, in which region the particle can be in equilibrium. Okay, right. I'm going to take the region 1 here. Let's take the positive charge again. Let's say Q. Okay, now this plus Q1 exert repulsive force in this direction. Okay, and this Q2 is also exerts repulsive force in the same direction. Is my point clear to you? Both the charges are of positive nature and this charge is also positive. So these two charges repel this charge in the same direction. So this charge runs in this direction. This charge flies away in this direction. That means this charge can never be in equilibrium in this region. Not possible. Not possible. Similarly, in this region also not possible, because both the forces acts in the same direction. Okay. Now, this is also not possible. Let's look at this region. Let's say I have placed the third charge somewhere here, Q. Somewhere here, Q. Now, this Q1 exerts repulsive force on this Q in this direction. Okay. Now, this Q2 exerts repulsive force in this direction. Q2 is trying to push this charge to the left, and Q1 is trying to push this charge to the right. That means there are two forces acting in opposite directions. So there is a possibility for the third particle to be in equilibrium, But what we need to do is we have to adjust the distance. We have to adjust the distance. How do we do that? We use basic concept of Coulomb's law again. So let's write the Coulomb's law. Coulomb force F is equal to K Q1 Q2 by R square. This is the force between these two. But I don't want the force between these two charges. I want the force between these two and these two, right? So I'm rewriting this equation. Okay. So F is equal to F1. I'm writing it as F1 K Q1 Q upon let's say X square. Okay. Now F2 is equal to K Q2 Q upon R minus X whole square. R minus X whole square. So if I use these two relations for these two forces, for the third particle to be in equilibrium, the two forces must be acting in opposite directions. With equal magnitude. That means these two forces must be of equal magnitude. As these two forces are acting in opposite direction, that we have identified. But we want to make these two forces equal magnitude. Okay. In order to do so, what we are going to do? We are going to adjust the distance. So, but we use our basic common sense. Where should we place in between the two charges? Third charge. Where should we place the third charge in between the two charges such that it will be in equilibrium? That means net force on it will be 0. Okay. To identify that, we are going to take the relation of Coulomb's law, force equation. K is constant. Q is there in both the equations. So this Q by X square and Q2 by R minus X square must be same for the two forces to be same, right? So since Q1 is less and Q2 is more than Q1, for the ratios to be similar or equal, this X must be less. Since Q1 is less, X must be less. For the ratios of these two terms to be equal, if this is less, this also should be less. If this is more, this also should be more. Then only the ratios could be equal. So by using the same concept, I am going to write the equations. F1 is equal to K Q1 Q by X square. So I have to place the third charge near to the smaller charge. So we have got two conclusions, actually three conclusions. For the particle to be in equilibrium or the object to be in equilibrium, at least two forces are required. and those two forces must be acting in opposite direction with equal magnitudes. I am going to write these points in the takeaway points. But anyhow, I am going to say it now. The two forces must be in opposite directions with equal magnitudes. First point. Second point. Second point. In this case, if the two charges are of same nature, either positive or negative, if the two charges are of same nature, then the third particle must be placed in between the two charges. In between the two charges, not beyond the two charges. Okay, these are the 2 points. Now the third takeaway is, the third charge must be placed near to the small charge. Then only there is a possibility for the occurrence of equilibrium. Okay, right. F1 is equal to k q1 q by x square, and F2 is equal to k q2 q by, if this is x, then this must be r minus x whole square. For the particle to be in equilibrium, these two forces must be equal in magnitude. So I am writing k q1 q by x square is equal to k q2 q by r minus x whole square. Let's simplify it. K gets cancelled, q gets cancelled. If I rearrange this equation, r minus x whole square by x square is equal to q2 upon q1. Let's simplify this further. We are going to arrive at the formula. Just remember that formula if you are unable to remember the entire process. R minus x by x whole square, is equal to q2 by q1. If I take out this square, I have to introduce the square root here. If I apply the square root on both sides, square will get cancelled, square root comes here. R by x, I am writing it as r by x, and x by x is nothing but 1 root over q2 by q1. R by x is equal to root over q2 by q1 plus 1. As I would like to find the equilibrium distance, the question is asked like, where should the third charge be placed such that the third charge will be in equilibrium. So my task is to find x. So x is equal to r upon root over q2 by q1 plus 1. So this is the equilibrium position of the third particle. Only third particle will be in equilibrium. Okay, net force on the third particle is equal to 0. For the third particle to be in equilibrium in this given scenario, when the two charges are of same nature, then the equation will be x is equal to r by root over q2 by q1 plus 1. Okay, hope this example is clear to you, right? Okay. Let's move on to the next example. Okay, I am going to define this example again. In the earlier example, we have learned that the charges are of same nature. Okay, but in this case, I am going to take minus q1 here and q2 here, plus charge. Now, in this case, the two charges are of opposite polarity. As we have three regions, region 1, region 2 and region 3. Among the three regions, in which region is suitable for the equilibrium position of third particle? Now the question is, where should the third charged particle be placed such that it will be in equilibrium? Okay, right. Let's verify that. Which region is suitable? Okay, let's say I've taken the third charge, capital Q again, plus charge, let it be. So Q1 is attracting this plus Q towards right, and Q2 is repelling this Q in leftward direction. Okay, there is a possibility, two forces in opposite direction. There is a possibility for the equilibrium of third particle. Come to the second region. If I place this charge Q here, this Q2 is applying repulsive force in the right direction, and Q1 is attracting this particle in the left direction. Here also equilibrium possible. Let's take the third case, third region. Q is placed here. Now, Q1 is attracting this charge, Q2 is repelling this charge. That means these two forces are acting in the same direction, so the charge Q will never be in equilibrium in between the two charges. Okay, here is possible, here it is also possible, but let's identify which reason is most accurate for the equilibrium. Okay, now as I have already mentioned, the equilibrium, the third charged particle must be placed near to the smaller particle, I am representing Q1 is less than Q2. Magnitudes I am taking as I have already. Okay, Q2. Since Q1 is less, magnitude of charge Q1 is less, so the third charged particle must be placed close to Q1 itself. Okay, close to Q1 itself. That means region 1 is correct, region 2 is wrong. Right? Whichever the charge is small, we need to keep the third charged particle near to that charge. If the two charges are of same nature, then the equilibrium position will be close to the smaller charge in between the two charges. If the two charges are of opposite nature, then the equilibrium position will be close to the smaller charge beyond the two charges, not in between the two charges. Okay, now I'm going to erase the entire, okay, I'm going to rewrite. This is minus Q1 and Q2. Equilibrium position will be somewhere here. I'm taking the charge Q. I'm considering this distance as X, and as I've already mentioned, the separation between the two objects as R. Now, two forces F1 is equal to K. I'm going to write the magnitudes only. K Q1 Q by X square, and F2 is equal to K Q2 Q by R plus X whole square. This time R plus X whole square. Now, for this third particle to be in equilibrium, F net must be equal to 0, which is possible only if the two forces acting in opposite direction, as we have already verified, with equal magnitudes. That means we have to equate these two magnitudes. That means K Q1 Q upon X square is equal to K Q2 Q by R plus X whole square. Now K will get cancelled, Q will get cancelled. If I want to simplify it further, R plus X by X whole square. I have taken this R plus X whole square this side as X square, and this term both has squares. I am taking square as common, and Q2 I am taking this Q1 this side, Q1. Okay. Now let's simplify it further. If I remove this square, I will have square root here. So R by X plus X by X is nothing but 1 is equal to root over Q2 by Q1. Now if I want to, I can take this plus 1 this side. R by X is equal to R by X is equal to root Q2 by Q1 minus 1. X is equal to, X is equal to, root Q2 by Q1 R upon root over Q2 by Q1 minus 1. So this is the equilibrium position of the third particle when the two charges are of opposite nature, where we have got plus sign if the two charges are of same nature. Okay, we have got two results here. X is equal to R by root over Q2 by Q1 minus 1. But as I have already told you, you need to consider the magnitudes only. Magnitude of charges only has to be taken in the formula, not with the signs, because there is square root. If you put negative sign, you will get error. Okay, this is a very good example for on equilibrium. Okay, hope this explanation or the example very clear to you. If you still find difficulty in understanding, please comment below. Watch it again for once or twice. You will be able to follow it. Okay, let's look at the next example. Okay, I'm going to define this example. Okay, right. As we have already learned two formulas here. If the two charges are of same nature, separated by a distance r, then the equilibrium position will be obtained between the two charges. Sorry, between the two charges somewhere here. Okay, x is equal to r by root over q2 by q1 plus 1. If the two charges are of opposite polarity, minus q1 q2, then x is equal to r by root over q2 by q1 minus 1. Okay, now let's use one of those formulas. Let's suppose minus q is this charge and plus 9q is this charge, separated by distance r, let it be. Okay, now as we have already learned the equilibrium position of the third particle, question is asked to find the equilibrium position of the third particle. Where should the third charger particle must be placed such that it will be in equilibrium? Okay, as we already know, the third charge particle must be placed near to the smaller charge. As we know, this is the smaller charge. The third charge particle must be placed near to this charge. So to identify which location, means as these two charges are of opposite polarity, there is no possibility for the particle to be in equilibrium in this region. So I have to place this third charge near to small charge beyond the charge. Okay. If this length is at separation is x, then f1, I am directly using the formula here. Okay, I'm directly using the formula. Now x is equal to r upon root over q2 by q1 by q1, as these two charges are of opposite polarity, negative sign plus minus 1 is equal to r. q2 is nothing but 9q by q1 is q root over minus 1. So if I cancel q and q, 9 will remain. Root 9 is nothing but 3. 3 minus 1 is 2. What am I getting? R by 2. So this will be our answer. Okay. So I have to place the third charged particle exactly at r by 2 distance, close to the minus q charge, beyond this charge, not in between the two charges. Okay. Hope this example is clear to you, right? Okay. Now let's move on to the next example. Right. So I'm going to define the example now. Okay. How are we going to define? Okay. Let's take equal charges q and q. Q and q separated by center to center distance is let's say 2r. Let's say 2r. Now what I'm going to do is I'm going to take another charge somewhere here exactly at the middle, because the third charge can be in equilibrium exactly at the middle, because these two charges are of equal magnitude and of equal nature. So the equilibrium will be obtained between the two charges exactly at the middle, because the two charges are of same magnitude. Now since the third charged particle is in equilibrium at the very beginning, now the question is asked, the third charge is in what kind of equilibrium? Stable, unstable, neutral equilibrium, or rotational equilibrium? Among the four, which equilibrium the charged particle is in? Okay, right. So the third charged particle is in. Okay. In order to identify that, what I am going to do is I am going to recollect the definitions of stable, unstable, neutral equilibriums. Okay. What is stable equilibrium? If I displace the particle from its equilibrium position slightly, if the particle comes back to its equilibrium position, then we say that particle is in stable equilibrium. If it is not coming back, rather it is moving away, then we say that equilibrium is unstable equilibrium. If it is not, if it is neither coming back nor going away, it is exactly where I have placed it, where its new location is, then we say that particle is in neutral equilibrium. Okay, right. Now let's try one of those. Okay, now what I am going to do is, this particle is in equilibrium. Now I am slightly displacing this particle to this point, okay, to this point. Okay, now I've slightly displaced and left it free. Now let's identify in which direction the particle moves exactly when I left it free. Okay, so as I've moved this farther away, the repulsive force between these two decreases as distance is increased. Okay, and the repulsive force between these two will increases as the separation between the two decreases. Exactly at this location, the force between these two, repulsive force and repulsive force between these two are equal. When I displace this particle to here, the repulsive force between these two decreases, repulsive force between these two increases. That means force in this direction is more than force in this direction. That means net force will be to the left. Therefore, this charged particle at this new location tries to comes to its equilibrium position, and obviously it moves between these 2 points like this, oscillates. Okay, as this particle is trying to come to its equilibrium, this equilibrium is called stable equilibrium. So that means it is in stable equilibrium. One question has been answered. Now coming to the second question. If it is making harmonic oscillations, what will be its frequency, what will be its time period, what will be its angular frequency? There is a possibility for asking such question. Okay, let's analyze this question even further. Okay, now, right, okay, let's say I have displaced for about x distance, slightly displaced. Okay, now let's find the net force at this location. Now this is charge 1 and this is charge 2. So force F1 is equal to K Q capital Q divided by distance is nothing but r plus x whole square. Remember, I have displaced it slightly. X is very small. Now let's write the equation for force due to this one. K Q and capital Q by what is this distance? R minus x whole square. Now what I am going to do is I am going to find the net force. That means F1 plus F2, minus F2. Both the forces are in opposite direction. F1 is K Q by r plus x whole square minus K Q by r minus x whole square. As we have common terms, K small q capital Q has been taken common, 1 by r plus x whole square minus 1 by r minus x whole square whole into, right? F net is equal to. Okay, let's simplify furthermore. Now I have F net is equal to K here Q. I am taking the LCM as this can be written as r plus x into r minus x, r plus x into r minus x. A plus b into a minus b is nothing but a square minus b square. So I am writing it as r square minus x square, as we have two terms, r square minus x square. I am taking this one out and squaring it up. Okay, right. Now if I find the LCM, r minus x whole square minus r plus x whole square whole into. Now if I simplify this equation, r square plus x square minus r square plus x square will get cancelled, minus 2rx minus 2rx, that means minus 4rx by r square plus x, r square minus x square whole square, right? Okay, since x is very small, x is very small, higher order terms can be neglected. X square tends to 0. If x square is equal to 0, then F net is equal to minus 4k q r x by r square whole square means r to the power 4. 1 r will get cancelled, 3 will remain. So what are we left with? Minus 4k q x by r cube, x by r cube. Okay, now we are going to use the harmonic equation F net, harmonic force F net is equal to F net is equal to minus k kx. Okay, so force in harmonic motion, so minus kx. If I equate these two relations, minus kx is equal to minus 4 k q x by r cube. Now this k and this k are different, so I'm cancelling this k, x and x. What am I getting? K is equal to, this minus will also get cancelled. 4, this small k is nothing but 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught q capital Q by r cube. Q capital Q by r cube. Now 4 and 4 will get cancelled. This k is equal to q capital Q and what is it? Q capital Q by pi epsilon naught r cube. Q capital Q by pi epsilon naught r cube. Okay, k we have got harmonic constant, SHM constant. Okay, now what I am going to do is okay, so what we are asked to find? Angular frequency first. Angular frequency. Omega is equal to root over k by m. I am considering the mass of the particle. Third particle is m. Mass of the third particle is m. Then omega is equal to, k is nothing but what? Q capital Q by pi epsilon naught r cube divided by m. Divided by m means m into root over. So omega we have determined as or derived as root over q by m pi epsilon naught r cube. M pi epsilon naught r cube. Now, as we know, frequency of oscillations. So frequency f is equal to omega by 2 pi, because omega is equal to 2 pi of, I have taken this 2 pi this side, so omega by 2 pi, so I am getting 1 by 2 pi. We already know omega, root over q by m pi epsilon naught r cube. Okay, now what are we going to do? We are going to find the time period. Time period t is equal to reciprocal of frequency, that means 2 pi root over m pi epsilon naught r cube by q. So these are the relations which we use to find the frequency, time period and angular frequency of the particle making SHM. Hope this explanation is clear to you. Did I make anything wrong in between the calculations and all? Since x is very small, x square can be 0. So if x square is 0, then did I leave anything? Okay, everything is clear here, right? 2 pi root over m pi epsilon naught r cube divided by q into capital Q, right? So this is how we can find the time period of oscillations made by the particle which is in stable equilibrium. Okay, now let's move on to the next example. Let's look at this example. Let's define this example. This charge is q, this charge is also q. Third particle can be in equilibrium exactly at the middle. I'm taking that charge as q and its mass as m. Okay, now what I'm going to do is I'm going to displace this third charge along the perpendicular bisector. Okay, perpendicular bisector. Now okay, now what I'm going to do is I'm going to displace this particle along the perpendicular bisector. Let's say till here, till here, till here. Okay. Now exactly what happens? This particle repels, this particle also repels. Okay. So let's say this is F1, this is also this is F2. Both the forces are same because the distances are same and charges are same. So if I resolve these two components, F1 cos theta, F1 cos theta, I mean F2 cos theta, F1 sin theta and F2 sin theta. Okay. As these two forces are same, these two will get cancelled. Net force is acting in vertically upward direction, so the particle will not come back. That means this particle is in unstable equilibrium. Unstable equilibrium. Now, instead of taking the positive charge, what if I have taken negative charge? What if I have taken negative charge? Let's do that. Okay. Instead of taking the positive charge, I have taken negative charge, mass m. Mass m. Let's say I have displaced this charge till here. Now the charge is somewhere here. Okay. What is the displacement? Y displacement, let it be y. Okay. Now what exactly happens is this charge is q, this charge is also q. Now this positive charge will attract this negative charge in this direction, and this positive charge will again attract this negative charge in this direction. Right? Right? Okay. Since it is a perpendicular bisector, these angles are same. Angles are same. Now what I am going to do is I am going to draw the x-axis and y-axis. This is y-axis, this is x-axis. Now if this force is F, this force is also F, since the charges are same and distance is also same. Okay, right. Now what is it? Perpendicular bisector. Perpendicular bisector. Now what happens? Since the net, I'm going to resolve the forces. F, if this angle is theta, this angle also should be theta, this angle also should be theta. F cos theta, and this component is also F cos theta. Since two forces are acting in opposite directions with same magnitude, cancel out. And how about this one? F sin theta, and this is also F sin theta. As these two forces are acting in downward direction, that means this charge which I have displaced will again comes back to its equilibrium position. Again comes down, again comes back to equilibrium position. It makes oscillations about mean position. It makes oscillations about mean position. Now, let's do the same exercise and find the net force equated to minus kx. Find the SHM constant and then find angular frequency and time period. Same exercise again. Okay, right. Okay, so the net force, as these two components have been cancelled, net force is equal to F sin theta plus F sin theta to F sin theta, which is equal to, as this force is acting in downward direction, I am going to apply the negative sign here. Okay, is equal to minus ky. In the earlier case I have taken x because the displacement is along x axis. In this case I have taken y because the displacement is along y axis. Okay, now minus will get cancelled, however. So 2 is there. F is nothing but the electric force between the two charges. Electric force K, instead of writing K, I am going to write 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Sin theta is equal to F is not completely written, right? So F okay, Q capital Q capital Q. Now this Q is somewhere here, right? So Q capital Q minus Q. I am taking the magnitudes only. Q capital Q by distance. This distance I am taking it as I am going to define the distance as well. Okay, I'm going to define the distance as well. Okay, so this distance is 2r. Distance is 2r. That means this distance is r and this is y. So here this distance will be root over r square plus y square. R square plus y square. Okay, now divided by r square plus y square under root square. Okay, k q1 q2 by r square. Okay, into sine theta. By looking at this, right angle triangle, right angle triangle, right angle triangle, this one, this right angle triangle. Okay, this right angle triangle. Sine theta is equal to opposite by hypotenuse. Opposite is nothing but y by hypotenuse is how much? Root over r square plus y square. R square plus y square is equal to ky. Ky. I am going to cancel this y and y. Okay. Now I am going to simplify even further. So 2 2s are 1 by 2 pi epsilon naught q, capital Q, square root get cancelled, and there is r square plus y square whole to the power 1 by 2, here whole to the power 1, that means 1 by r square plus y square whole to the power 3 by 2 is equal to k, is equal to k. As I have already told you, I have displaced the particle slightly, very less. Y is very small. Y is very small. Y is very small. Okay, y is very small. Y is very small. Y is very small. That means y square tends to 0. Y square tends to 0. Then what are we left with? Then q, capital Q by 2 pi epsilon naught into y square is 0. So r square whole to the power 3 by 2, square and 1 by 2 get cancelled. R cube will remain. R cube will remain is equal to k. Is equal to k. Okay. Did we do any wrong? Sin theta whole to the power 3 by 2 r cube k. Okay. Now, now angular frequency. Angular frequency. Angular frequency omega is equal to root over k by m. Root k is how much? Q by 2 pi epsilon naught r cube into m, into divided by m, it can be taken to the denominator. Okay. Now frequency f is equal to omega by 2 pi. That means f is equal to omega by 2 pi in the sense 1 by 2 pi root over q by 2 pi epsilon naught r cube m. Okay. Right. Now time period. Time period t is equal to reciprocal of frequency. So time period t is equal to reciprocal in the sense 2 pi root over 2 pi epsilon naught r cube m by q, capital Q. So we have derived the equation for time period of oscillations, frequency of oscillations of the particle which is making SHM or simple harmonic motion about mean position along the perpendicular bisector. Okay. In the first case, I have taken positive charge which was initially at equilibrium, but if I displace this object, that particle along the perpendicular bisector, it is not coming to its equilibrium position back, rather it is moving away. That means it is in unstable equilibrium. Okay. Now instead of taking the positive charge, I have taken the negative charge this time. Now what happens? I have displaced this negative charge and I have identified the net force. This net force is causing the particle to come to its equilibrium. That means the negative charge can be in unstable equilibrium. So I have used the concept of stable equilibrium. I have used the concept of stable equilibrium. I have determined the net force on the particle and I have equated it to net force, which is SHM force ky. Now simplified those equations in order to get the final result for frequency and time period. So this is how I have analyzed the concept of equilibrium of the charged particle which is negatively charged in our case, when it is displaced along the perpendicular bisector. Hope this concept is clear to you. If you find any difficulty in understanding the concept or the steps that I have followed, please comment below. If possible, watch it for twice or thrice. You will be able to follow it. Okay, right. Let's move on to the next example. So let's discuss another example. This will be our last example on equilibrium in collaboration with Coulomb's law. Let's define this example first. Let's take the charge minus q, and this is 16q, 16 times q, separated by a distance r. Separated by a distance r. Now the question is asked like, what amount of charge and where should it be placed such that the entire system of the three charges should be in equilibrium. In this case, not like one charge will be in equilibrium. In this case, we have all charges should be in equilibrium. Okay, so in order to solve it, crack it, let's understand the question first. As there are two opposite polarity charges are given, one of them is small, one of them is large. As we already know from the analysis and basic common sense, the third charge must be placed near to the small charge and beyond the small charge, right? So I am considering the equilibrium position is somewhere here. I am taking the third charge as q. We will understand whether it is positive or negative in a bit. Okay, and this equilibrium position I am taking it as x, that we are going to find. Okay, so to find this x value I am directly using the formula. X is equal to r by root over q2 by q1 minus 1, which is r by root over 16q by q minus 1. As I have already told you, this q2 and q1, even though negative charges are given, we need to use the magnitudes only. Okay, 16q, root over 16 is 4, 4 minus 1 is 3, so I am getting the equilibrium position as r by 3. So first result has obtained. Now the question is, what kind of charge is to be placed and what amount of charge is to be placed. Now in order to find the amount of, nature of charge, let's use our basic common sense and the basic understanding of Coulomb's law. If this is, let's say, minus q, if this is negative, let's say negative, then what happens? So first of all, we have to mention that this capital Q should be in equilibrium and minus q should also be in equilibrium, and this 16q, sorry, and this 16q and this 16q should also be in equilibrium. For the entire system of charges to be in equilibrium, the plus q, minus q, 16q, all the three charges must be in equilibrium. Okay, equilibrium means net force on each charge must be 0. We already know capital Q, net force on capital Q is 0, because we have used the same concept and we have derived the equilibrium distance as well. Okay, now let us find the net force on minus q. Okay, so if I have taken negative charge, then can the net force on minus q be 0 if I would have taken negative charge? Okay, this negative charge is pushing this negative charge in this direction because there exists repulsive force, and this 16q charge positively charged, and this is negative charge. This 16q is attracting this negative q charge in the same direction. That means both the forces are acting in the same direction. There is no possibility for the equilibrium if this third charge is negative. Instead of taking the negative sign, let's say I've taken the positive sign. Okay, I've taken the positive sign. I've considered this third charge is positive. Let's analyze the net force on minus q. Net force on minus q is 0. Can possibly be 0 or not. Okay. This positive charge attracts this negative charge in this direction. Okay, well and good. Now this positive charge again attracts this negative charge in this direction. That means there are two forces acting which are in opposite direction, and if I change the charge here, I can get equal amount of charges. That means I can balance the forces. That means I can make this net force on minus q 0. Okay, right. So for the net force on minus q to be 0, force due to plus q, force due to 16q must be same, equal and opposite. So force on minus q due to plus q is equal to force on minus q due to 16q must be equal in magnitude, opposite in direction. Okay, now I'm writing the equations k q. I'm taking the magnitudes only, I'm not using the negative sign. K q q by what is it, distance is x, x is nothing but r by 3, r by 3 square is equal to k q again 16q by what is the distance, r square. Okay, is that clear? Right. Now to simplify this, I'm cancelling the common terms. Q and q will get cancelled, r square will get cancelled. What are we left with? What are we left with? Capital Q is here, and 1 by 3 square means 9 will come here, is equal to sorry, 16q. Okay, now capital Q is equal to 16 by 9q. Capital Q is equal to 16 by 9q. As I've already told you, this capital Q is positively charged. I'm introducing the positive sign here. So if I place, if a charge plus 16 by 9q is placed at r by 3 distance from minus q charge beyond, then all the three charges will be in equilibrium. I haven't determined the net force on the third charge. You know why? Because if the net force on this charge is 0, net force on this charge also 0, then the net force on this charge also must be equal to 0 from the superposition principle. Okay, because the net force acting on the entire system is 0. Okay, so this is how all the system of particles, all the three particles of all the three charges will be in equilibrium in the given system. I hope this example is clear to you. Okay, if you find any difficulty in understanding this, please comment below. Okay. Okay, now based on the examples that we have explained or followed in this lesson, in this session, in this lecture, let's take some points, key takeaway notes from this lecture. Okay, now okay, right. So first point, we have understood that for the system to be in equilibrium, at least two forces are required. At least two forces required. At least two forces required for the system particle here to be for the system to be in equilibrium, and the two forces must be equal and opposite to each other. Okay, this is one key takeaway notes. Second one. Okay, third particle will be in equilibrium in between the two charges, two like charges. Like charges in the sense positive or negative. I'm drawing the diagram here. If this is positive q1, positive q2 or negative q1 negative q2, then the equilibrium will be in between equilibrium point. Equilibrium point will be observed in between the two charges. Okay, now third point, same point again. Third particle or charge will be in equilibrium beyond the unlike charges. That means one charge is positive, other charge is negative. Okay, I'm drawing the diagrams for better understanding. Minus q1 q2, one is negative, another one is positive. There is no possibility for the equilibrium in between the two charges, rather it appears beyond the charges. That means it may be somewhere here or here depending on the quantity of the charge. Okay, equilibrium. Okay, or equilibrium. Okay, now fourth one. Equilibrium is closer to small charge. Whichever the charge is smaller, the equilibrium lies close to that charge. See, I am taking an example q1 q2, and I have taken the condition q1 is greater than q2, then the equilibrium lies close to this q2 because q2 is smaller charge. Equilibrium. If this is something like minus q1 q2, and this time I have taken q1 is less than q2, let's say, in such case the equilibrium lies somewhere here, close to the smaller value and beyond the value, because two charges are of unlike charges. Okay. Now last point. Okay, fifth point. For the third particle to be in equilibrium, third charge in equilibrium, the amount of charge does not matter. The amount of charge and nature of charge does not matter. So these are the very, very, very important key takeaways from this entire lesson. Okay, I hope the explanation provided in the session or the lecture is very helpful to you, very clear to you. If you face any difficulty, if you feel any difficulty in understanding the explanation, please watch it again. If you still feel difficulty in understanding, please comment below. Okay, so I hope this video is helpful. If you find the video is helpful, please like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. So that's it in this video. Thank you for watching. See you in the next video.